For the benefit of those who don't know much about this, I'll cover some bits and pieces that I think pretty much anybody who doesn't know about this will need. So this is really an introduction to the MAMS designs. A lot of the details of the practical side of this and how the software works and so on will be covered by subsequent speakers. So I'm just going to concentrate on the basic ideas here. I think Max has given a pretty good idea why we need new trial designs, and like Max, most of my practical experience in trials comes from cancer. So there's a little bit of a cancer focus in my talk, but in principle it shouldn't be limited in that way. So I shall say a little bit more about the benefits of cancer treatments, and then I shall go on to talk about outcome measures, which are kind of a critical issue for these MAMS designs. There are two types, as we know. There's the intermediate and the definitive outcome, and Paul has already raised a question about surrogacy and so on, which I shall say a little bit about, but not a lot. I want to give an outline of a two-stage trial design and an example, actually an early example in some detail in ovarian cancer, and then I shall make some other remarks. If you wish to interrupt, I think that's okay. The person who's filming the session, Dan, is it okay if people interrupt during the session, or doesn't it?
Yeah.
It's fine. Okay, so if you want to raise a question, that's fine. Okay, so we know a little bit about this already, of course. We know something about the fact that several treatment regimens may be ready now for evaluation in phase 3 trials, but there's often a narrow window of opportunity for these trials. Something can quickly get out of date, particularly in the fast-moving world these days. So we want to get on and test these treatments quickly. We know that most new treatments are no better than the previous ones were. And also we want to try and minimize exposure of patients to ineffective treatments if we can do that. And often these ineffective treatments also turn out to be much more toxic. For example, very high activity chemotherapy regimens in cancer are often very toxic. Obviously resources are always limited, so we do need these more efficient designs. And the key here is the comparison, of course, of several treatments with control, not just one treatment. Most cancer treatments are modest in their benefit, actually. The mortality rate is typically reduced by the order of 15 to 30%. In other words, in terms of what statisticians may be more familiar with, a hazard ratio of around 0.7, 0.8, or even a little bit more than that, is quite a common result in a cancer trial these days. Just to give an idea in cancer for what you might call the 3 different stages of cancer, I've called early, locally advanced, or local spread of a tumour, and advanced cancers. The effect size you can see is given there of the order of 20 to 30% reduction in event rates, but the number of patients can range quite widely from at least 2,000 or more actually in early cancers. Breast cancer is not unusual these days to have 3,000 patients or more, and in advanced cancers they tend to be smaller, but for the early cancers the time frame is horrendous, and as Max said, maybe 3 trials in a lifetime for a breast cancer clinician is quite realistic. Now going on to a little bit more about the designs, I want to say a little bit about these so-called intermediate and definitive outcomes. In what follows, when I'm talking technically at all, I shall be using notation for I standing for an intermediate outcome and D for a definitive outcome. And what a definitive outcome is what we would usually call the primary outcome of a trial. It might be overall mortality, or it might be cancer-specific mortality, or some other type of time to event outcome. So what we assume here is not so much that I is a surrogate, which is a very strong requirement of an intermediate outcome measure, but more that the intermediate measure is on the causal pathway to death particularly. So whatever causes death is also going to affect the other outcome, the intermediate outcome. And because of the way we define this, it's the usual situation is that treatment effects, if they exist, if there is a treatment benefit, for example, tend to be correlated between the 2 types of outcome. And the absolutely canonical example in cancer is that the intermediate outcome is an event for the progression of the disease or to death, and that D, as I said earlier, is death itself. So it's pretty obvious that if a cancer spreads, it's on the causal pathway to death. I mean, this is quite clear. There are other situations where it may be less clear, and then one has to be very careful and think about that. So why do we want to use this, or why indeed we even consider using an intermediate outcome measure when we've already got a definitive one in mind? Well, basically because it increases the power or the speed of the trial. Typically, these intermediate outcomes, and this is fairly clear, I think, will have a higher hazard, and more likely to occur earlier than the definitive outcome. And sometimes, actually, we get another effect, which is that you might have a slightly larger treatment effect on the intermediate than on the definitive outcome. That isn't as common as you might think, but it can occur, I believe. So both of these two types of factors increase the lead time on the time to an event of some kind being observed. And here is an example of that coming up on the next slide from an earlier trial in ovarian cancer, ICON 3, which was completed a good number of years ago now, but the basic principle is still the same. So what I've got here is a Kaplan-Meier survival plot from this trial, and you can see that 5-year survival in this condition is pretty low. This is advanced ovarian cancer. But what we see here is that the upper graph, which is the time to death from any cause, and the lower graph, progression-free survival, are very different. And indeed, the median time to event is something like 1.5 years for progression and 3 years for death. So there's a large lead time for events in this particular condition. Now, coming on to a so-called MAMS design, we struggled a bit with the with the acronym for MAMS. We don't really like MAMS very much, but at least it's become established now, so we can say it. You know, it's not one of these things where you've got 17 letters and you have to say them one after the other. So a two-stage. I'm just going to give an example in a two-stage design, and the generalization, if you like, to multi-stages is not particularly difficult. But I think it's quite nice to have just a two-stage design. It's easier to explain. Hopefully, it'll be easier to understand it. So we've got a two-stage design. We've got two types of time to event outcome, the I event and the D event. We've got an outcome measure which is pretty standardly used in cancer, and another time to event study, which is the hazard ratio. I don't want to go into the details or about questions about non-proportional hazards at this stage. This may come up. We have some experience of it, but let's stay within the proportional hazards framework for now. So we're looking at the hazard ratio, treatment divided by control. And obviously a good treatment reduces the risk, and on the way this is scaled, that would have a hazard ratio of less than 1. Some people do it the other way around, so bear in mind that lower means good. And then we have a number of treatments, which are generically called E, experimental research arm treatments, that we want to compare with a standard of care or control treatment, C. The stage 2 trial has two stages, of course. The first stage is what you might call a lack of benefit analysis. So basically what we want to do, the aim simply is to say, okay, we've got a treatment, it's compared with control, it's not doing very well, even at this relatively early stage, and we don't want to continue putting resources into that arm. We want to cease recruitment to it. And so we carry out an analysis that allows us to do that on the intermediate outcome measure, stage 1. So that's a lack of a benefit analysis, and I'll say a little bit more about that, how that works in a minute. So for any of these experimental treatments that make it through to the second stage, then we look at the real question, which is on the definitive outcome. However many treatments are left in the design are then compared with the control arm in the usual way. So it's really not a very complex concept, really. So the way this works for the two stages individually, how would this go? So we'd randomize patients to the control arm and to each of the experimental arms. We tend to use the same allocation ratio for each experimental arm. I think the software requires that, as I recall. It doesn't have to be 1-to-1, but it's always got to be the same bit for each experimental arm. So then we start the trial. Everything's set up. We start the trial until we continue until we observe a certain number that I've called EI for the number of events on the intermediate outcome in the control arm. And then we perform an analysis of the data we've got so far on the intermediate outcome. And what we actually do is to say if the hazard ratio for a given arm on the intermediate outcome is less than some threshold called delta I there, then we say, okay, there's some evidence here, the HR, the hazard ratio is a bit less than our threshold, or maybe it's a lot less, and therefore that treatment looks promising and it passes to the next stage. And if that isn't the case, if the hazard ratio is too big, maybe it's 1, for example, showing no difference, then further patients are not recruited to that arm. We continue to follow those patients up. They're still in the trial, but there's no further patients added to that arm. If all the treatments failed to pass the lack of benefit analysis, then we stop recruitment altogether. And that essentially is the end of the trial, though we may continue to follow patients up. What are these threshold numbers, such as the number of events in the control arm, EI, and the delta I? Just to give you a feel for this, a flavour from the very earliest trial, they used, I wasn't involved at this stage, they used a cutoff of 0.87 for the hazard ratio, which I think was kind of halfway between the target value of 0.75 and the null value of 1, something like that. And the number of events was less than you would perhaps normally expect to have in a fully fledged trial, 250 at the intermediate stage. Okay, that's stage 1. So if stage 2, the second stage, patients are still continued to be recruited, of course, to the control arm and to all the experimental arms that passed the first step. We use the original allocation ratio, that doesn't change, but the numbers of patients going to each of these arms may change, of course, if some have been omitted. And we continue this accrual process until we see a certain number, ED, of definitive events in the control arm. And these events are, of course, combined over the first 2 stages together. Having got all this, we then do the usual significance test, typically a log rank test, on the hazard ratio for the definitive outcome for every surviving experimental arm. And a typical example is that we might be having a target hazard ratio for efficacy of about 0.75, as I mentioned earlier. Now, okay, so we've got this 2-stage approach. We've got 2 different types of outcome. How on earth do we specify this? There's an awful lot of, potentially a lot of parameters to think about here. It's bad enough with a single-stage design. Well, early on, I was thinking about that. I was worried about this because when this design was first introduced, I hadn't seen it before. It took me some time to realise actually what we needed to do was to simply take it as though there were 2 independent trials being designed here. One stage 1 trial and one stage 2 trial. The stage 1 trial is worked on the I events, the intermediate ones, and the stage 2 trial is designed on the definitive events. And if you work through that, that turns out to be quite a convenient and understandable way of doing things, because kind of it's familiar, but also it can be worked with. And what I mean by it can be worked with, if you want to know the overall, for example, significance level and power, which obviously you will want to know that, for the whole design, including both stages, how do you do that? Well, I mean, the first thing you have to assume, and I think this is important, is that I mentioned it before, that the treatment effect, the hazard ratio, or the log hazard ratio on both of these types of outcome, the intermediate and the definitive outcome, there has to be a correlation between these treatment effects. There should be a correlation. If there isn't, then you do worry about the surrogacy, if you want to put it that way, or whether it's a valid intermediate outcome. So we're going to assume there is a correlation. And then having got that, the actual overall type 1 error and power depend only on the correlation and on the individual stages of the 2 pseudo trials that you've got. So how do we specify the first stage, quotes trial? Well, this is what we tend to design these things pairwise, even though we may have more than 2 arms. Power and significance level is what we have to look at, of course, for a design. And what we want is for the power, we want the power to get past the threshold to be high here, because we don't want to filter out by mistake by making a type 2 error with a too high probability. We don't want to filter out good treatments at this intermediate stage. That would be a disaster. So we want to have a high power, higher than we're usually used to, and 0.95 is a number we often work with, typically. So that gives us a good chance that an effective treatment will escape this barrier and get through to the next stage as it should. In terms of the type 1 error, the significance level alpha I for this, first thing to say is we want it to be one-sided, not two-sided, because we're not interested in experimental treatments that are worse than control at this stage. We don't want to know about that. So we use a one-sided significance level, which is a bit unusual. Just an aside, that the actual significance level we use here tends to control how long stage 1 lasts. The more stringent it is, the more events are required, and the longer stage 1 has to last. So that's quite an important consideration in practice. And also what's unfamiliar here is this type 1 error, this alpha I, can be quite large, larger than we're used to. For example, it could be 0.25, and we've even worked with larger values than that. And why are we allowing it to be quite large? Because basically, if we make a type 1 error, what does that mean? It just means a treatment that isn't too good gets through to the next stage. Okay, we waste some resources in allocating patients, which we shouldn't, but it's not a disaster. Whereas screening out a good treatment which should have got through is a disaster. So this is what's guiding these alpha I and power I parameters. As far as the target hazard ratio, we usually use the same value as we do for the definitive outcome. There is sometimes, excuse me, a case to be made for using a more stringent value for this, but generally we haven't actually done that. So we usually target the same hazard ratio as for the definitive. The second stage the second stage is similar to a usual trial. So for every pairwise comparison, we just do the usual calculations, and we work with, let's say, a one-sided 0.025 level for the significance level, which is 5% two-sided, of course. Power 0.9, that's what we usually do in our trials here. And in practice, yes, as I said, each surviving comparison will be at the 5% level, two-sided. How do we calculate the overall type 1 error significance level and the power for the trial, for the two-stage trial? Well, the first thing that comes up, of course, is how on earth do we get this correlation? We've got a correlation between two treatment effects. Well, if we do the trial once, we haven't got lots of repeated trials. How do we know what the correlation is? And what we've done to try and get a handle on this is basically to work with previous trials in the same disease, similar setting, not identical. It never will be identical, of course. And from that we can use the bootstrap to get an estimate of the relationship between the log hazard ratios for the two types of outcome. And that works pretty well, we think. I'll show you an example in a minute. Obviously the treatments have to be somewhat related to those in the new trial, otherwise we're not looking at like and like. And what we find when we do this analysis, I'll show you some examples in a minute, is that the correlation between the hazard ratios, log hazard ratios, is typically of the order of 60%, 0.6. That's what this parameter rho is. Having got that, then we can do some rather simple mathematics to show what the overall type 1 error or significance level is, which is the expression alpha equals 5,2 of blah, blah, blah. Now, what that means is basically those z values are the normal equivalent deviates of the significance level, and in the intermediate outcome and the significance level for the definitive outcome, rho is the correlation. And it turns out that area under the bivariate normal distribution function is the right expression for the overall significance level. This is assuming that the log hazard ratio estimates are normal, which they are, roughly. Similarly, for the power, we just substitute the normal equivalent deviates of the power calculation in there. So that gives us an overall type 1 error and so on. Here's the example I mentioned, bootstrap analysis of the ICON 3 earlier trial in ovarian cancer. And here's an example showing what the bootstrap distribution of the log hazard ratio for the overall survival on the y-axis versus the same thing for the intermediate outcome PFS on the x-axis. And you can see that there's a beautiful bivariate normal type elliptical scatter, and that really works quite surprisingly well. Some examples of the sorts of correlations that you'll find in real studies. Again, these are all in ovarian cancer, different studies. The trial I just mentioned, the correlation is about 0.6. A meta-analysis also in ovarian cancer, we found about 0.7, and another ovarian cancer about 0.6. So this is fairly consistent. Okay, so let's now look at a 5-arm trial. Sure.
Obviously, the extent to which progression-free survival is correlated with overall survival,
Yeah.
presumably therefore the hazard ratios, depends on the overall survival from the disease. So, for example, pancreatic cancer,
Yeah.
progression-free survival is very similar to overall survival, whereas in breast cancer they're really quite different.
Mm-hmm.
Have you got any idea, illustrative correlations for other cancers?
Have we got any? Does anybody know? I don't know the answer to that.
Yes. We have carried out, similar studies to see the range of the correlation of several diseases. Breast cancer, as well, for example. as Patrick suggested, in most of the practical applications we looked at, in breast cancer, colon cancer, or brain cancer, it ranges between 0.4 to 0.6. It's the range. I have we looked at this. I don't know whether you want to.
No, I think that's right. Yeah, 0.6 is in situations where they appear to be well correlated. 0.6 is a number that commonly emerges.
Yeah.
Yes, in most scenarios it's 0.6. Various diseases.
But the other point is which we've done, is you can do a sensitivity analysis, of course, over a range, and usually I'll show you a little bit more about this in a minute. The effect of that. Yes. Could you mind giving your name?
My name is Jim Paul.
Oh yes, okay, thank you.
Does the power, to some extent, not only depend on the strength of the association?
Yeah, I want to show a bit of it. Yeah, I'll show you that. It's coming. Yes, Dan.
Does the correlation not depend on how far apart the analyses are anyway?
Yes.
And the algebraic calculation for anyway, is the bootstrap necessary?
Okay, so the question was whether the correlation depends on how far apart the two analyses are, and the answer is yes, it does. If you look at that example there, which I didn't say, which is on the screen, is that this is with 200 intermediate events, 250 definitive events. Well, that implies a timeline for that, of course. And so if I'd said 100 I events and 300 D events, it would have been a longer timeline between them, and therefore because of that, you'd expect the correlation to be a bit lower, actually. So yes, it does depend, and you have to be sensible about that. But this is where the role of some kind of a sensitivity analysis helps you, actually.
That will come up in another presentation.
Okay, good. All right. Any other? No. Okay, so let's just go on a bit more about the operating characteristics of the design. Let's think about some generic 5-arm multi-arm trial, and let's look at the pairwise comparison between any experimental arm and control over 2 stages. So what is indeed the significance level and power for this situation? So this is now coming straight back to the question I was just asked about the correlation. So let's give an example where you've got a type 1 error alpha I of 0.1, 10% in the first stage, and a 0.025 at the definitive stage. And let's suppose the power was 0.95 for the first and 0.9 for the second. Well, here's 3 different values of the correlation. I wouldn't want to work too much with a correlation of 0, but let's see what happens if we do that. And then a low correlation of 0.3 between the 2 treatment effects, and a higher correlation, typical number, 0.6. So what we see there is that the overall significance level is one-sided is about 0.003 when there's no correlation, and goes up to 0.014 when there is a moderate correlation. So the significance level, and this is what we usually find, we'll always find in fact, the significance level depends quite strongly on the magnitude of the correlation. By contrast to that, the power hardly depends on the correlation at all. You can see the power is nearly 0.87 in all cases. So that's that situation. Yeah.
Could I just ask, the alpha here is a single pairwise alpha. That's not adjusted for any multiple testing?
It is not adjusted for multiple testing at all.
And is that an issue?
It could be an issue. Can we come back to that as a question? If that isn't picked up, raise it again, please. Yeah? Okay, so that was the pairwise situation. Now I want to also continue looking at the overall situation. What is the chance of rejecting the null hypothesis when it's true for any arm? This is a family-wise. This may be more what you're thinking about. Family-wise significance level. And the sort of comrade of that is the family-wise power, which is the chance of rejecting H0 under H1 for all the arms. And this is 1 minus the chance of making a type 2, any type 2 error, basically. So those are one of our other speakers will say something more about this, I think. So the family-wise thing, here is the family-wise thing, and now what we find, exactly the same 3 scenarios with 3 different correlations. The power and the significance level now both depend on the correlation a bit. And of course the significance level is higher than it was before. If you've got a good memory, you'll probably remember that the significance level was quite a bit lower than that. Let's go back to the trial. There we are, 0, 0, 3, 7 and 14. Now we're looking at 9, 22 and 41. Okay, obviously larger. And the power is lower, of course. And again, it depends a little bit more on the correlation. Just one, I must have made one note on here that the alternative hypothesis that the arm is effective with a hazard ratio of whatever 0.75, it's unlikely that will actually be true for all the arms, in fact. So this situation is sort of very much an extreme case. But it gives you some feeling. Okay, so those are sort of some of the really nuts and bolts of this design. What about even more basic stuff? How many patients do I need? Well, we need to know this, of course. So how do we get a handle on this? Well, the first thing we, of course, must ask, as in all trials really, how many patients can I expect to recruit to the trial per year or per time unit? In that ovarian cancer trial, we discussed ICON 5, there was planned to be 1,000 patients, which is quite unusual actually. But you need to know. The other thing that's obviously critical is how likely it is to get an eye event or a D event in the control arm. And we need to know that because obviously the higher the hazard, the shorter the trial will be. One thing that we're going to assume here is that the distributions of time to event is actually exponential. Now this helps to plan the number of events accurately. If it's not exponential, it will affect the timelines a bit. But we have to make progress with the maths for this. Okay, so from the design parameters that I've talked about, we can calculate the number of things that we need. Number of eye events, ER and ED, which we've discussed already. You can get the total number of patients out of the design by some mathematics, and you can also get some idea of how long stages 1 and 2 are likely to last, which is important for planning. Just to show you a little bit of some of the mathematical background, in your pack you'll find a paper published in Trials 2011, I think, which goes into all the mathematical details of this stuff for a 2-arm trial. So you could think of it as for a given pairwise comparison, we want to know how all this was worked out. It's all in the paper. So this is just one very small element from the paper. And it just shows how you can calculate the number of events expected after a certain elapsed time as a function of the hazard of an event in that arm, whatever it was, and time itself. And you can see it involves R, which is the recruitment rate of the patients, and it involves the hazard, and it's quite a simple expression. But actually things get much more complicated once you start adding more stages. For 2 stages it's rather easy. So as I just said, I'm going to repeat myself, similar calculations but more complicated, you can use to find the number of events for the D and the time for the D outcome, given the parameters for that. You can also do a little tweak whereby you might want to take into account stopping the trial a bit early. You don't necessarily want to continue recruiting to the very end. You might stop and then observe for events, and you can feed that number, which I've called T-stop, into the design to tell you when to stop recruiting patients. And you can, as I said earlier, you don't have to have a 1-to-1 allocation ratio. Okay, so the ICON 5 trial is an example. This was an early trial we did with this design. 4 complicated, complex chemotherapy regimens were compared against best standard of care. And this was an international trial which we coordinated with centres all over the place. America, UK, Europe and Australia. This is the sort of generic MAMS diagram that's been around for about 10 years, I think. It's really essentially shows what Max showed in his diagram. There you can see you've got the control and 4 research arms going to a PFS assessment stage. Some of them may continue and others not. And then the ones that continue are tested at the end. So that's in essence a MAMS design for 2 stages. These are the parameters that were actually used in the trial. These were, I think, the concept was right, but some of the parameter choices are pretty much like this, I think. Is that correct, Max?
I'll never admit that.
Right. Okay, they were highly carefully worked out parameter value. Anyway, those were the numbers that we used. And perhaps one thing that's noteworthy here is that the alpha that was used, the alpha I, which as you can see under the column stage 1 was 0.064. That's the number that turns out to be the value you actually get when you use the threshold, this intuitive threshold of 0.87 for the hazard ratio. So 0.064 is actually quite a bit smaller than we would normally recommend nowadays. And actually also we've got a higher power at the final stage. I don't quite understand why the power is as high as 98%, which is most unusual. Anyway, that's what happened. Okay, so with the chosen design, let's assume the correlation that I talked about earlier is 0.6. The overall type 1 error turns out to be 1.1%, and the power of 93% for each comparison. With one expected experimental arm, just one, the duration of the trial would be 4.5 years with 4,500 patients. But if you then said, oh, I want to do 4 two-group trials sequentially, one after the other, to test all these 4 comparisons against control, all on their own with a one-sided significance level of 1.1% and power of 0.93, then it would take me over 11 years, and it would take over 11,000 patients. So this is a crude description of how you might save an awful lot of time with the MAMS approach, a lot of patients. In the event, this trial was reported a number of years ago, it actually recruited a lot faster than expected. I think the recruitment rate was more than 1,200 a year. It was very popular. Stage 1 eventually was performed, the analysis on the PFS, and actually, sadly, none of the 4 experimental arms passed into the stage 2 analysis. And the hazard ratio for all these chemotherapy regimens was between 0.94 and 1.07. So you can see why none of them passed the 0.87 threshold. So at that stage, then the trial terminated but it already accumulated 4,300 patients. So in some sense, ICON 5 was a vast success of the technology. In another sense, it was a failure because all the experimental treatments were no better than control. But I think we learned something from that trial. I'm going to stop in a few minutes because I can see time's ticking on, but just to address a few outstanding points here, I've already said that if you've got more than 2 stages, the same principles apply. The mathematics is much harder. A PhD student of ours, Sophie, finished some time ago, and she basically tackled this stuff, and we've refined it a bit for the trials paper that you've got there. There is, thank God, software to do all this work, which we're going to see a bit of in a minute. It's called End Stage. That was published for Stata in 2009, and has been updated a bit since then. And the sort of flagship MAMS trial that we're running at the moment, as most of you may know, is in prostate cancer, which will be described by Matthew Sides shortly. That's a 6-arm trial, and it's even got an extra arm at the moment, and it's going to have another arm. So it's really quite a complicated piece of work. There are a few issues still sitting there which we're looking at. I've mentioned the family-wise error rate. I think the best way to deal with this is simulation, and we're going to develop software to do that. There are questions that arise from the way we've tackled the design. For example, some people might say, well, why not start from the overall significance level and work backwards to the individual stages? We're thinking about doing that, but we're not sure yet whether it's even feasible or whether one should be doing that. So your thoughts and reflections would be helpful on that, if you have any. Another obvious extension of the design is to cases where you have more than just, or differently from just, time to event outcomes. For example, the intermediate outcome could be binary. In cancer, that could be tumor response to a treatment, for instance. And the definitive event could still be time to event. We are making some progress on these various issues, and I'm sure there are plenty more that will be needed to be looked at in future. Thank you.